Section 1.1.9 Cloud Economics OPEX versus CapEx, and why this shapes architecture. Up to now, we've been talking about how cloud systems behave, how they scale under pressure, how they fail, and how engineers deal with trade-offs as systems grow larger and more complex. But behind all of those technical decisions, there is another force quietly shaping architecture. It doesn't appear in diagrams, it isn't visible in code, yet it influences design choices just as strongly as performance or reliability ever could. That force is cost. Not cost as an accounting concern, but cost as a technical reality. Because in real systems, architecture choices are never theoretical. Every decision you make eventually shows up somewhere, often as a very concrete number on a bill. Once you start looking at systems through this lens, many modern architecture decisions stop looking arbitrary and start looking inevitable. At a high level, organizations have traditionally paid for computing infrastructure in one of two very different ways. For a long time, the dominant model was capital expenditure, CapEx. In this model, infrastructure is bought up front: physical servers, storage hardware, networking equipment, entire data centers. A large investment is made in advance, and the equipment belongs to the organization. This is how classic on-premise environments work, and it's still common in banks, telecom providers, factories, and government systems. Working this way forces organizations to plan far ahead. They estimate their highest possible demand and buy enough capacity to survive that peak, even if it only happens occasionally. This approach has real strengths. You have full control over your environment, costs are predictable over long periods of time, and you are insulated from sudden pricing changes or provider decisions. But it also comes with an unavoidable limitation. Because systems must always be ready for the worst case, they are almost always oversized. Most of the time, large parts of that infrastructure sit idle. They still consume power, still require maintenance, and steadily lose value through depreciation. Idle capacity often looks harmless on paper. In reality, it quietly drains money every hour. Capital expenditures reward stability and control, but it does so by locking decisions in early and making change slow and expensive. The cloud introduced a very different way of thinking. Instead of owning infrastructure, organizations rent it. This is the operational expenditure model, OPEX. Compute, storage, networking, and managed services are paid for as they are used. When usage goes down, cost goes down with it. And that single shift reshapes how engineers think about systems. Instead of asking, what is the maximum load we must survive? The question becomes, how closely can this system follow real demand? Let's make this concrete. Imagine a service that needs 20 servers during peak hours. That peak happens for 2 hours a day. The other 22 hours, it needs 5. In a CapEx world, you buy 20 servers, and you pay for all 20, every hour, every day, all year. In a cloud OPEX world, you pay for 20 servers for 2 hours, and for 5 servers for the remaining 22. Nothing about the software changed, only the economic model did. And that single difference quietly reshapes architecture. This is where an important realization appears. Elasticity is not just a technical feature, it is an economic mechanism. This is also one of those ideas that comes up again and again in interviews. Not as a trick question, but as a way to check whether someone understands the cloud as a system, not just as a collection of services. Scaling up matters, but scaling down matters just as much. In an OPEX model, idle resources are no longer invisible, they are billed. This is why teams are often surprised by their first cloud invoices. The system works perfectly, but it costs more than expected. Not because the cloud is broken, but because inefficiencies that used to be hidden are now fully exposed. A very common scenario looks like this. A company moves an existing application to the cloud. The architecture stays the same, fixed server counts, always-on instances. Databases sized for peak load, running 24/7, nothing breaks. Performance is fine. But the monthly bill is suddenly far higher than expected. Not because the cloud is expensive, but because the system was designed for ownership and is now being paid for as usage. Once you see this, certain engineering practices stop looking optional. When a service shows consistently low CPU or memory usage, that is rarely a harmless safety margin. More often, it points to fixed instance counts, overly conservative auto-scaling limits, or components that never scale down. In the cloud, unused compute is not a neutral state. It is a constant cost. The same logic becomes very visible with managed databases. Here, cost grows with CPU usage, memory consumption, storage size, and especially I/O. Inefficient queries, missing indexes, or poorly designed schemas don't just hurt performance, they increase your bill every hour. When database costs rise faster than traffic, the root cause is almost never the cloud. It's usually the way the system is using the database. Networking adds another layer to this picture. Moving data into the cloud is usually cheap. Moving data out is not. Over time, this pushes architectures toward processing data, where it already lives, instead of constantly exporting it elsewhere. In cloud environments, architectural inefficiencies don't remain theoretical. They show up clearly, in metrics and in invoices. Two broader concepts help explain why this model spread so quickly. The first is total cost of ownership, TCO. TCO includes far more than hardware or service pricing. It accounts for operations, maintenance, upgrades, staffing, and risk. In cloud environments, much of this operational burden shifts away from the organization and toward the provider. The second concept is return on investment, ROI. With CapEx, ROI is slow. Large investments are made up front and recovered over many years. With OpEx, ROI is faster. Teams can start small, experiment, and scale only what proves valuable. This difference explains why startups and new products adopted the cloud so aggressively. Of course, the cloud is not universally better. There are cases where CapEx is a rational and even superior choice. When workloads are stable and predictable, when latency requirements are extremely strict, when regulations demand full control over data, or when hardware is highly specialized. This is why many real-world systems mix approaches. Hybrid architectures are not compromises. They are economic optimizations. Over time, all of these forces shape architecture in very specific ways. Compute becomes ephemeral. Storage becomes durable. The two scale independently. Stateless services become easier to scale. Auto-scaling reduces waste. Containers improve resource utilization. Serverless systems eliminate idle cost entirely by running only when something actually happens. These are not trends, and they are not stylistic preferences. They are direct responses to how systems are built. If there is one idea worth remembering from this section, it is this. Cloud architecture is not just about building systems that work. It is about building systems that continuously adapt, technically and economically, to how they are actually used. Once you truly see that, many design decisions stop looking arbitrary. With this, we complete the cloud mental model. Next comes the layer that connects everything together: how software moves from idea to production, how it is deployed safely, and how feedback loops shape quality. That layer is DevOps, not as a buzzword, but as engineering logic. End of section 1.1.9.